Okay, today we're gonna cover section 6.4 work. In this section, we're gonna start the work. Work is the total amount of effort required to perform a task. Such a okay. The force F on the object is can be written as m times the second derivative of s, which is the position function. A force of 1 Newton acting on a mass of 1 kilogram produces an acceleration of 1 meter per second square. In a first course in physics, you typically look at the work that a constant force, F. If the net force F is equal to ma acting on an object is constant, then the object's acceleration a, which is the second derivative of the position function s of t, is a constant. Okay, so you must see in this. This is the Einstein's formula. Okay. In this, so in this case, the work done is defined to be the product of the force F and the distance d that the object moves. So work is the force times the distance moved. So W is equal to Fd. So F is equal to m times the acceleration, and W is the F times d. Okay, that's the two formula that you should know in this section. The unit for W is a Newton meter, which is called the joule, J. Okay, and we assume the acceleration due to the gravity is 9.8 meter per second square. We denote it as a G. First example, find the work done in lifting 1.4 kilogram book off the floor to put in on the desk that is 1.0 meter high, like this. Lifting a book from the floor to on the desk. Okay. Then, how much work is needed to do the task? First, from the first formula, F is equal to ma. In this case, what the acceleration is gravity, because we are in the nature situation on the Earth. So F can be written as m times g. Here, the mass is 1.4 kilogram, and g, gravity, is 9.8. So F is 1.4 times 9.8, which is 13.72, for 13.72 Newton. Okay, we are looking for work, which is F times D. F times D. Since F was found as 13.72, and the distance moved is 0.8 meter, so we multiply 13.72 and 0.8, which is approximately 10.976 joule. So that's the work which is needed to do the task. Okay. Next, variable forces. However, most forces are not constant. Before, the acceleration was constant, but in most of the cases, the forces are not constant and will depend on where exactly the force is acting. So, let's suppose that the force at any x is given by f of x. Then the work done in moving the object from A to B can be found with this definite integral. W is equal to integral from A to B f of x dx. To see a justification of the formula, we may take a look on the proof here. Here is the proof of this formula on work with variable force. Okay, here. So this is the formula that we introduced now. So the work done by the force F over the range on A and B is this, because of this reason, like what we saw in the Riemann sum, and the limit process gives us limit sigma as the integral, and delta x becomes to dx, which gives us. So we just divide the interval and find the small the section of the works and added them, and then we take a limit process to get the whole work done. And this is what we have learned in the earlier section that can be found by the definite integral like this. Okay, so now we have this formula to find the work with the variable force. Okay, particularly if the force is constant, then we get the correct formula for the constant force. If these are constant, then this f times f integral a to b f dx can be written in this way, and this is f b minus f times b minus s, where b minus s is simply the distance moved d. So it's just w is equal to f d. So this the earlier case is a special case of this general case. Okay, now we introduce one example of non-constant force. Here, find the work done in moving a particle from x is equal to 1 to x is equal 5 when it is located at the distance x meter from the origin. A force of ln of x Newton acts on it. Okay, find the work. And when we have the force f of x is equal to ln of x. So as we see, work can be found at the definite integral from 1 to 5 with the f of x, which is ln of x. So all we have to do is just find this definite integral, which can be easily calculated as 5 times ln of 5 minus 4. So the work done is 5 ln of 5 times ln of 5 minus 4 joule. Okay, that's it. So you can find the work. You can find work for whatever work at the force is done, is given. Next, Hooke's law. Yeah, you must be familiar with this spring business. The force f of x required to maintain a spring stretched x unit beyond its natural length is proportional to x. So f of x can be written as k times x, where k is a positive constant called the spring constant, provided that x is not too large. Okay, see figure 1 here. So this is a natural length. Then if you move if you pull it over, then you need some force to do so. Okay, so let's think about the problem. A spring has been stretched from its natural length of 20 centimeter to a length of 30 centimeter by a force of 40 Newton. Then find the work done in stretching the spring from 40 centimeter to 50 centimeter. Okay. Okay. So by Hooke's law, we need to find the constant K, spring constant K. Okay. Here, since a force of 40 Newton was required to stretch a spring of 10 centimeter, because natural length was 20 and it's been stretched to 30, so the difference was 10 centimeter. So we needed 40 Newton to make the stretch of 10 centimeters, which is 0.1 meter. The Newton is Newton meter is the right measurement. Okay. So now we have so 40 Newton was used to make the 0.1 meter distance, the first times the constant K. So K should be what? Divide 40 with 0.1, so K should be 400. So now we have a force f of x as 400x. Okay, now what we need is the definite integral. W, the work can be found by the definite integral of 40x. From where to where? Let's see. From where to where? So, now the work done in stretching the spring from 40 centimeter to 50 centimeter. So we need to measure. First we need to convert these into distances from natural length in meters. Okay. So doing that gives us axis of 0.2, because original distance was 0.2 centimeters and it was started from 40. So the difference was 20 centimeter, which is 0.2 meter. From there to 50 centimeter. So the difference from the original length is 30 centimeter. So the ending point is 0.3 meters. So we started from 0.2 meter and ended at 0.3. So the work done can be found as an integral of 400x dx from 0.2 meter to 0.3 meter, which can be found like this. And because x, antiderivative x is x squared over 2, so 200x squared is the integral, and so from 0.2 to 0.3 gives us 10. So the answer, the 10 joules of work was done to do this job, to stretch 10 centimeters of the given spring. Okay. Example 4. We have a cable that weighs 2 pounds per feet attached to the bucket filled with coal that weighs 700 pounds. The bucket is initially at the bottom of 500 feet mine shaft. So now we are in the mine. We are now full over the bucket of coal from the bottom to the top. Okay. Determine the amount of work required to lift the bucket all the way up to shaft. Okay. So we wanna find the work needed to pull over the bucket with coal from the bottom to the top, which is distance, whose distance is 500 feet. Okay, so this is the situation. So the situation can be formulated in this way. Okay. Okay. In this case, the force will be the weight of the bucket and the cable at any point in the shaft. To determine a formula for this, we will first need to set a conversion for x. Okay, for this problem, we will set x to be the amount of the cable that has been pulled up. Okay, so at the bottom of the shaft, the x should be 0. Then at the top of the shaft, it should be 500, which is a ground level. Okay, and so also at any point in the shaft, there is 500 minus x feet of cable still in the shaft. You understand? Here is the mine here, the poles are here. We want to put it over this from here. So we like to put it over this one of 500 feet, like into the weight of 700 pounds. Okay. So how much of work is needed to put this over? So the distance is 500. Okay, we start from here. The 500 minus x is the distance of the cable. Okay. So force. So the force then for any x is then nothing more than the weight of the cable and the bucket at the time, at the point. That is, f of x is the weight of cable plus weight of bucket with full of coal. Okay. So here, so the weight of cable, which is 2 times 500 minus x plus, so cable is the weight of this one and weight of this one. So 2 should be multiplied. And plus 700 pounds of the bucket with coals. So 1,700 minus 2x is the force that is needed. So work can be found as an integral of this f of x dx. Integral f of x dx. From where to where? From 0 to 500. From bottom to the top. So all we have to do is find the integral of 1,700 minus 2x from 0 to 500 with respect to x. With respect to x. So that's just 1,700x minus x squared from 0 to 500, which is about 60,000 pound. Okay, work. The last problem. A tank has a shape of inverted circular cone, height 15 meters and base radius 4 meters, and is filled with water to a depth of 20 meters. So this is a tank. It's a cylindrical tank, circular cone tank. Circular cone tank with of height 15 meters, and filled with water is filled with about this much, with 12 meter height. Determine the amount of work needed to pump all of the water to the top of the tank. Okay, we wanna pump all of this water in the circular cone from out of the tank, circular cone tank. So we need some work to do the task. Assume that the density of the water is 1,000 kilogram per cubic meter. Okay. In this case, we cannot just determine a force function f of x that will work for us, because this problem was introduced by the Paul Dawkins, and this is a very typical example of this case to find the work done. Okay, in this case, we are going to need to approach this from a different standpoint. let's first set x is equal 0 to be the lower end of the tank or cone. And x is equal to 15 to be the top of this cone tank. Okay. X is from 0 to 15. With the definition of our axis, we now see the water in the tank will correspond to the interval from 0 to 12. Now the water is filled in here. So let's start off to dividing 0 to 12 into n subintervals of each of width delta x. And let's xi star be any point from the ith subinterval where I is in between 1 to n. So this piece, this red bar, this divided the water into n layers. So whole the water was divided as n layers like this. The ith layer is approximated by the circular cylinder with radius Ri and height delta x. Equally divided by delta x is divided by n. So this interval 12. Now, for each subinterval, we will approximate the water in the tank corresponding to that interval as a cylinder of radius Ri and height delta x. What is the volume of this layer, of lead layer, in the cylinder, in this cone, it is cone-shaped tank, circular cone. Okay. Here, so let the lead strip in the sketch represent the cylinder of water in the ith subinterval, like this. So a quick application of a similar triangle will allow us to relate this Ri and Xi star as follows. The ratio of the Ri over Xi star should be 4 over 15, because 4 over 15. This is this is similar, so we can set up this equation. So Ri can be written as 4 over 15 times Xi star. Then the mass Mi over volume of the water and volume of the water Vi for the ith subinterval is simply what? This mass is the volume times the density. Mi is the volume of this times the density of the water. So we now know the density of water as what? 1,000 kilogram per cubic meter. So it was given in the problem. And because we are approximating the water in the ith subinterval as a cylinder, we can easily approximate the volume. Okay? So volume Vi is what? The Mi can be found as density times Vi, and Vi can be found as what? It's a disk. So pi r square times the depth, the height, the delta x. So this gives us a volume. So volume times the density gives us the mass, Mi, and then all the mass can be the summation of the masses of these each sub-intervals. Okay, now we are all set. We have Vi, we have Mi, and we have the equation of Ri with respect to Xi. Okay, so so the mass for the ith subinterval can be written as this. So Mi is the density times volume, so density times Vi. So density is 1,000, and Vi is a pi r square times the delta x, which is the depth. So this is the Mi, which can be simplified in this way, because Ri is the 4 over 15 times Xi star. So it can be written as 640 over 9 times pi times xi square times delta x. This is mi. Then, what is the force and what is the work? Force is the mi times gravity, g, for Fi. Fi is mi times gravity, and work Wi is the F times the Fd. Okay. So we are all set. So here the F is here. 여기에 this is Fi. Okay. Fi is equal to mi times g, and g is 9.8, the gravity. So Fi is equal to mi times g, which is approximately 9.8 times this mi here. 640 over 9 times pi times xi square times delta x. And then so we have Fi now. So we need Wi, which is Fi times the distance. Then once the distance moved, we have the 15 meter high height. So in order to reach the top of the tank, the water in the ice subinterval will need to travel approximately 15 minus xi star from this point to the top. Okay, it should be moved to put it over to reach the top to the tank. So the distance can be written as distance moved can be written as 15 minus xi star. So this is a d. So Fwi is the Fi times d, which is 9.8 times 640 over 9 times Wi is Fi times 15 minus xi star, which is this times 15 minus xi star here. So total amount of work required to raise all the water to the top of the tank then be approximated as a summation of each of these Wi's for I is equal to from 1 to n. So W is a summation of all of those. By adding those. And then this W can be, and then we to get the actual amount of the work, we simply need to take n goes to infinity. We make the slice, the depths as many as possible. So let's send n goes to infinity. Then complete. This W can be found as the limit of this. So limit integral can be translated to the integral limit summation to the integral delta x goes to dx here, and the interval traveled from 0 to 12. So 12 minus, so W is the integral of this f of x from 0 to 12. So this is a simple integration of x square, which is okay here. As we see here, W is Fi times 15 minus xi star. So here we should have, since F is this is F, so we should have 15 minus xi star here, and W should have this times 15 minus xi star here, and this W is a limit summation this times 15 minus xi star here, and so W is the integral from 0 to 12, this times x square times 15 minus x, and here x square minus x square times 15 minus x, which gives us the integral as the 15 over 3x cube minus 1 over 4x fourth from 0 to 12. So this value gives us this. So there was a mistype of this here, 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 and here, and here. And then we have the w as the integral of f from 0 to 12 with respect to x to have 7,562,362.543 joule is the answer that you are looking for. Okay, anyway, as we have seen in the previous example, we sometimes need to compute incremental work and then use that to determine the actual integral we need to compute. This idea does rise on occasion, and we should not forget it. So that's the technique that you may have to use it. Okay, but once you get a formula, the computation is not difficult. Here's the last example with the computer algebra system. Okay. A particle is moved along the x-axis by a force that measures 3 over 1 plus sine x Newton at the point x meters from the origin. Then find the work done in moving the particle from the origin to the distance of 3 meters. Okay, so the distance from the origin to 3 meters. So this particle moves from 0 to 3, and the force was given as this. So the f is this, f of x is this. So w is the integral from 0 to 3, f of x dx. It's like this. So we can easily compute this to get this. Let's do the simulation. Let's do the simulation. Okay, by copy this. And you see. So the integral of f of x, which is 3 times 3 over 1 plus sine x, then integrate this f of x with respect to x from 0 to 3 gives us the answer like this, which we have here, which we have here. Okay. And also the earlier computations of all of these, and all of others can be done without much difficulty. So since you already know f is equal to ma and w is the integral from a to b f of x dx. So now, yeah, you can whenever you fix the mathematical formula, the model of the given situation, then work can be found by the definitive integral of this. So in order to set up this formula, you should understand the given situation to set up a mathematical computation. Okay. And here, this shows you. So yeah, this single cell shows you the work, flow and flux in vector field. So we have covered the work in R2. So this is all single variables, but you will see the work in with the multi-variables like this, and as the different functions like this, then you can find the work, and you can see you will see the changes of the situations. This arrow shows the quantity of the work done, and this arrow shows the directions of where those works and flows move, the acting with certain amount of the force. Okay, so we will cover it in the multivariable calculus when you do it. And this photo shows one of the recent field medalists who was Asian. Okay, here are some problems, exercise problems that you're supposed to do, and here is so as you see, here you know the formula W is equal to Ft, and the work that you can find, and by the integrals, and for the constant case, the acceleration case, and the variable acceleration cases, and whatever the problems that you face, if you set up the formula, then you can use the template. You can use the sage command that you have seen to do all the computations in here and whatever. So all you have to do is just set up this set up the mathematical equations from the given conditions to do it. Okay. Okay. And here there's also another field medalist who won the field medal in 2006, about 8 years ago. He was also Asian Australian, and now Asian American at UCLA. And he gave Terry Tower, who was one of the well-known genius, and he gave a plenary talk in recent Korean math science meetings, and his wife is Korean too. Now, Korea will have the International Math Congress in next year at Seoul, and we will see another new field medalist, and we hope to see some of the familiar faces in that ceremony. Okay, I think that's the end of section 6.4. We now have 6.7. Is there any questions on work?